We're going to pick up on chapter 2. We covered horizontal and vertical motion, and now we're going to talk about the three laws of motion. So, the three laws of motion were first detailed by Sir Isaac Newton, who is a very prominent scientist in the field of physics. So, we hear a lot about Newton's scientific research and discoveries in our discussions of physics. Now, this would have been in about 1564 to 1642 AD. That was during his lifetime. And along with physics, these laws of motion, Newton was also working on calculus, which is a specific kind of field of math, as well as a law of gravitation that we're going to see at the end of this lecture. He published his findings in a journal article called Principia, and his essential idea was all focused around forces, with the exception of calculus. So Newton's first law of motion is often called the law of inertia. And so remember, we talked about inertia. It was a measure of an object's ability to resist change in motion or to begin to move. So if something's at rest and it's really heavy, it's going to resist a change in motion. And if something is really heavy and it's moving, it's going to take a lot of force to make it stop. So for example, if you're driving on the interstate and an 18-wheeler is next to you, and that 18-wheeler is fully loaded, has a heavy load it's carrying, it takes a lot of time and distance. It's one of the things you learn in driver's ed. It takes a distance and a lot of time for that 18-wheeler to stop, whereas your car or your truck may be traveling at the same speed as the 18-wheeler, but it can stop in a much shorter distance. And that's inertia. The same thing is if you are sitting at a red light next to an 18-wheeler and you both take off at the same time, you're probably going to be able to gain speed faster than the truck. So Newton's first law officially states that every object retains its state of rest or its state of uniform straight line motion, so moving in a straight line at a constant speed, unless it's acted upon by an unbalanced force. So meaning the brakes, the accelerator, something like that that's unbalanced. And the inertia will resist any change in motion. So if you're at rest, that's preferred to stay at rest unless an unbalanced force begins to act on you. And if you're moving in a straight line of motion, you're going to continue that unless you have an unbalanced force, which in some cases will be friction. So Newton's second law says that forces cause accelerations. And so there is a formula for Newton's second law, and it's F equals m times a, where m is the mass of the object, and a is the acceleration of the object, and F is going to be force. Now, the most common units of force are going to be newtons, which makes sense because he's the scientist that we're attributing most of these discoveries to. And the actual symbol is going to be capital N. So there is a proportionality constant if we're comparing two different situations, meaning if we hold the mass constant, so we're pushing the same object, we know that if we apply a larger force, we're going to get a larger acceleration. You push harder. But if we don't hold the mass constant, we know that if the mass gets higher and it gets heavier, it's going to be harder to make it accelerate as fast. So here are some images. So comparing figure A and B, you have 35 pounds worth of boxes on this dolly, and then in B you have 12 kilograms of weight of objects on this dolly. And so if you knew, okay, well, in this one there are 35 pounds and this is 12 pounds, you could anticipate that you're going to have to apply a higher force to figure A's dolly in order to get it to move, whereas figure B might be a little bit easier. And the same thing is true about making it stop. It's going to take more effort to make figure A's dolly stop than figure B. So as the mass goes up, you have to increase the amount of force in order to get an acceleration going. And same thing if you're a visual person, then another example would be if you've ever seen somebody trying to push a stalled car or something that ran out of gas, it is very difficult because that car is very heavy versus an empty grocery cart, super easy. They're both on wheels. Theoretically, they both roll downhill without any effort, unless you have the brakes on the car, but one takes significantly more effort in order to get motion going. So weight and mass. At the beginning of this, we kind of alluded to the fact that weight and mass are not the same thing. We use them interchangeably. We do not talk about your weight. And sometimes in science, we use the terms weight and mass interchangeably. What's the weight of the object? When we might really mean mass. So mass is the quantitative measure of inertia. It's how much matter you're made up of. Whereas weight takes into account the force of gravity acting on that mass. So here on Earth, we talk about weight. When you stand on a scale, you are measuring your weight, not your mass. So for example, if you're on Earth and you weigh 110 pounds, your mass is actually 50 kilograms. And there are some places where people refer to their weight in kilograms, their body weight in kilograms, which is a mass, and not their weight. Now, if you went to Mars, where Mars has a different gravity, it doesn't have a gravity of 9.8 meters per second squared like we do. And so the mass on Mars is going to be 50 kilograms because we're not changing up how much matter you're made up of. You're still going to be the same human with 2 arms and 2 legs and a head and the same everything. Nothing's changing about your body composition. But the weight is going to be less because the force of gravity on Mars is less, significantly less than on Earth. So the only time a measure of your mass is going to be different is if you actually lose part of your body. Otherwise, whether you're on the moon, the Mars, Earth, Jupiter, Saturn, the sun, floating out in space, your body's always going to be made up of a certain mass. The weight, on the other hand, is going to change depending on the force. So the way this works is force equals mass times acceleration. Mass is always going to be units of kilograms. Weight, on the other hand, because it takes into account gravity, the formula for weight is actually mass times gravity, which we've already talked about gravity's value of 9.8 meters per second squared. So if you want to know what your mass is, you're going to take your weight and divide it by the value of gravity, and that tells you what your actual mass is made up of. It's kind of the same reason why when you get in an elevator, you feel the different sensations when you're going up and down. When you go up the elevator, you feel like your body is being pulled down to the ground because it's increasing the gravity on your body. Versus when you go down in an elevator, you might feel like a little bit of a weightlessness, and that's because you're kind of counteracting that force of gravity a little bit. So Newton's third law of motion says that the source of a force is other objects, and that they're equal to each other. So when one force is applied to one object, there's an equal and opposite force applied back. So the third law relates forces between two objects, which is important because in our world, most objects that are moving come in contact with something else. So the official definition is whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. So for example, you have here the force of the satellite on the astronaut and the force of the astronaut on the satellite. And so when an astronaut might push off on a satellite, the forces are equal and opposite. So they're both going to float off in opposite directions. Now another example would be if you've ever played baseball or softball, when you have the bat and you get ready to hit the ball, and you hit the ball, and the ball goes out into the field, well, when you make contact between the ball and the bat, there's a brief moment of time where they're going to interact with each other. The bat is putting force on the ball, and that's going to cause the ball to go out, but the ball is also pushing back on the bat at the same time, which you can feel when you're holding it. It's not you're not unaware that you've hit the ball because there's no force. Same thing if you are pushing on a wall, you're applying a force to the wall, but the wall is also pushing back on you. When you shut a door, it does the same thing. You're shutting the door, you're applying a force, but the door is pushing back on you. So all forces between two interacting objects are equal and opposite. So that brings us to momentum. It's an important property closely related to Newton's second law. So if we go back and look at second law, it's relating force and mass and acceleration. So momentum includes the effect of both motion and inertia. So the momentum of an object is going to be equal to its mass times its velocity. And so the interesting thing about momentum is you can have an object looking down at this image right here. You have an astronaut who weighs 60 kilograms and a satellite that weighs twice as much, but their velocities are going to be different. The astronaut who's lighter is going to travel faster than the satellite who's heavier. So when we calculate the momentum by multiplying the mass and the velocity, we see that they both have a momentum of 45 kilograms meters seconds. So they're equal. And that is because the momentums of the velocity of the object is going to be closely related to its mass. Heavier objects are usually going to travel a lot slower, and lighter objects are usually going to travel a lot faster. When you fire a cannon or a gun, the same thing occurs. You have the velocity of the bullet, because it's very light, it's going to travel very fast. But there's still going to be some pushback on the gun or the cannon, but because the cannon or the gun is significantly heavier than whatever object it's launching, its velocity backwards is going to be very slow. It's still going to push back. Sometimes it pops people in the face, and you can see a cannon's going to jump back, but it's not going to move as quickly as the object that's been fired. So we call this conservation of momentum, which we saw in the last slide. 45 kilograms times meters seconds for the person and the same value for the satellite. So according to the law of conservation of momentum, the momentum of expelled gases in one direction equals the momentum of the rocket in the other direction, if we're in the absence of external forces. So for example, this rocket's taking off, and it's combusting some type of fuel in order to go out into space, and all of the gases that are being expelled are going to equal the momentum of the rocket, which is then going to launch it into space. Okay, if that wasn't true, then the rocket may not make it all the way into space. So this is going to end our discussion for right now. So take a break and then come back and finish up the lecture of chapter 2.